What's that? Just hit spacebar and type in. All right, we got, just for a heads up guys, we have today and after school today to continue with volume revolving. On Thursday we're going to do a different type of volume, which is more of a surface volume. A little bit more complicated, just for a heads up. Stuff that we're doing now should be a little bit easier. Most of the time you see the stuff that we're doing now in the exam. I did notice on like 2 practice exams that they actually did have ones where it was a surface volume, which is very different, and I'll explain that more in detail on Thursday. I actually wasn't even going to go into that. It's not really seen much, but I saw it on one exam, so I feel like we should cover it in case it comes up, okay, in case it is a topic. All right. So, just to recap for yesterday, let's go through a quick example. Okay, let's go through a quick example of yesterday. So if we have y equals x squared, yes, I am, thank you. Well, let's say, let me write it as a word problem. This is how you guys would see it. I'm just writing the equations up. F, the function f of x equals x squared is revolved around the x-axis and contained by the lines x equals -2 and x equals +2. Determine the volume of the solid produced. Okay, determine the volume of the solid produced.
I don't understand why basic working equation works.
Well, YouTube is getting restricted aspects of Can you guys just slide over a tiny bit so she can watch that one? Yeah, there's a chair over there.
What's the library?
Yeah, I thought you were going to read a book.
I want to see a part of it though. Because it's important I want to understand. What's the introduction to it?
Oh, you're lucky. The function f of x equals x squared is revolved around the x-axis and contained by the lines x equals -2 and x equals 2. Determine the volume of the solid produced. So what's the first thing we said yesterday that we should be doing right away? Good. Think about graphing it. Absolutely. So start by doing it this way in your head. Isn't that the graph right there? You agree? Y equals x squared. From 2 to -2. So I know that there's going to be some sort of limitation here and some limitation here. What's the first thing people would say about this? What are you noticing? What are some key characteristics about this graph that we're going to look at? There's 2 parts to it, right? Good. And what do we know about those 2 parts, Karen? Okay. Good. We're going to revolve. We're going to get them hollowed out. Yeah, but these are the same 2. Very good. So when I do this, I'm going to eventually revolve it like this, right? That's what the revolution is going to look like, actually. See that? That's the shape I'm going to get. I'm going to get this solid. Okay, I'm going to get this solid shape that I could think of as, I could think of it as one of those yo-yos. Not the regular yo-yo, the Chinese one. Absolutely. But one thing I want you to notice is symmetry. Everybody see the symmetry? Y equals x squared. So do I need both volumes? You could really just do the volume from 0 to 2, right? And then double it. Or the volume from 0 to -2 and double it. Or just do the whole volume from -2 to 2. Either way. Last name?
No, I just didn't know.
Yes, you do. I forgot that. That's my fault.
You should actually go let me in. It's like,
No, you should. That's fine.
No, it's gonna be in there. No, she needs to know just.
I look at shoes.
Yeah. We're gonna be there for like in the team or anything.
Is it not loading over there?
I'm just wondering if it'll be faster as mine.
The connection is the same no matter where you are, because they're all wired, so it won't make any difference. You're welcome to go there, but it doesn't matter.
It's called derivative of integrals, right?
And we have from there.
So we take the integral. So we take this, we take the, like I would, it's just so messy over there. But so we take the integral, and then we take our formula that we use, and then we just cut it out.
Yeah, but we gotta actually go through that
What is
now.
the R?
So,
No,
The
another
R.
R. Another Y.
let's look at this example, guys, because I feel like we're still confused from yesterday. What's the radius of any of these circles? The function itself.
Oh,
Again.
squared.
Here, we start by drawing in a radius, please. Draw the radius in right here. Between those 2 points. That's the radius. At any disk. Any of these disks has a radius of f of x. So if I want the volume of a circle, it's f of x squared times the pi. Okay, remember, volume of any cylinder or any prism is always the area of the base times the height. Well, the area of our base is a circle, pi r squared times the height. Well, r squared, the radius here is really f of x. So this is really pi times f of x quantity squared. What's the height again? What's the height of this? What did we call it yesterday? Delta x. But since we're integrating, we call that what? Dx. Because each of these, think about it this way, guys. This is really like a little disk right here. And its width, the width of that disk, is really delta x. But as I add all these little disks up over and over, that's where my integral comes in. It's the idea of a Riemann sum. You're adding up all those little rectangles, and you get the integral. By adding up all the widths of these little disks, I get the dx. So this becomes dx, and I take the integral from -2 to 2. Okay, to be more clear, because I know it's in the middle of the page, let me write it down here. So in this problem, I have the integral of pi times f of x, that quantity, squared, dx, from -2 to 2. Again, I could have done it from where to where also? 0 to 2, and what do I put on the outside, Carrie? A 2, because I double it, because of symmetry. Now, at this point, are we good? Can we figure this out on our own? Okay, quickly. Okay, it's x squared squared. Don't forget about that. X squared squared. Oops. Now, here's my suggestion for you guys. Plugging in a 0 is pretty simple, isn't it? So I would have done that personally, just to give you a heads up. Again, I would have done this, just so you are all clear. I would have done this. Okay? I would have done it that way just because it's easier for me to plug in a 0. It just drops off. What's 2 to the 5th? 32 divided by 5? Some decimal value, right? So we're going to get 2 pi 32 over 5. What do I write next? Thank you. Units what? Cubed. Good. Oh, that's why you was looking down. It's cubed, cubed, cubed. Volume, right? Three-dimensional world. Okay? So this would be my answer for this kind of a problem. Now, let's get to an AP problem now. That's not an AP problem. Okay? I know, I wish, right? Not an AP problem. All right. What if we have a problem where we have an intersection of two functions and they cross over? You asked about earlier. Okay?
Piecewise, this.
Absolutely. It's absolutely. So let's say we have well, let's start with an easier example. Find the volume produced by the region R. It's always said like this in the AP exam, the region R. By the region R when revolve around the x-axis. Remember, if you're doing the y-axis, it's the same thing, but we have to use dy and use our y limit to make everything in terms of y. We'll talk about that more. Find the volume produced by the region R when revolved around the x-axis if the region is defined as, let me get the right terminology. The intersection use, or is it term use? As the, oh, okay. On the exam, they actually give you a shape. Okay. If the region R is defined as the area between the functions, now I want to make one that works pretty well. F of x equals x squared plus 1 and g of x equals 2x. Okay? And g of x equals 2x. Start by graphing, please. Sketch them on your paper. Or graphing a calculator. This kind of a problem would probably be a calculator problem. A lot of the volume problems, they do turn out to be calculator problems. You just for a heads up on that. And I do have to look at the whole function. It could be negative, right? It could have a negative side over there for x. There's no problem here. And the line 2x, what is that going to look like?
Going up.
Going up, right? Where does it intersect here?
1, 1.
Wait.
How do you know that? Plug in a 1 here also, right? Inspection. Plug in a 1. You get 1 plus 1 is? Plug in a 1 here, what do you get? 2. That's another way to think about it. But I would set them equal, yes. So we're going to see that we're going to have something like this. And I'm assuming they're going to connect again at some point, right? I'm pretty sure they cross over one another point here. Quadratic growth is faster than linear growth, so eventually they'll catch up and turn back around. Is it tangent? Tell me it's tangent. Yeah, tangent. That's why. Okay. Do 2x plus 1. That's fine. Sorry about that. That's why, because it was tangent. That's my fault. So let's do an example of 2x plus 1. Okay. So we definitely have 2 intersections there, I think. Should be a secant, right?
Yep.
All right, so we got the region R that we're trying to figure out. We're trying to find the volume produced by that region R just flipping around the axis, or rotating around the axis. So, got some tough stuff going on here. Remember yesterday we did radius outer, radius inner, that stuff? It's going to come into play here clearly because look, we have 2 different functions. So, if I want to revolve this, first of all I need to know where they intersect, right? That's always my starting point. Where do they actually intersect? Okay, how do we know this? What are we doing? Set them equal, right? Set them equal like this. When I set them equal here, what happens to the ones? They both cross off. I'm going to get x squared equals 2x. I'm going to move the 2x over. I'm going to factor out an x. So yeah, but then you're going to miss one of your roots, Gary. You're going to get x equals 2, right? But where's the other root?
0.
Don't forget about that root. If you can do that, that's fine, Gary, as long as you remember. Remember, when you make a t-chart, you get 2 roots, really? So they intersect right here. So this graph is clearly not drawn correctly. They intersect at the point 1, 0, which is the y-intercept.
What's the range of intervals?
Okay, and then they intercept again at 2, whatever that value of that point is. Now, which way am I revolving around, the x or y axis? So do I care about the y values right now, actually? Because again, I'm looking to go from here, which is 0, to here, which is 2. So when I do my integral, I'm going to integrate from 0 to 2. If I was integrating this way, or if I was taking a volume this way, I would need to know the y value there, right? Which is 1, it turns out. And I need to know the y value there, which happens to be 5. 2 squared plus 1 is 5, or just 2 times 2 plus 1 is 5. So I'd have to go from just 1 up to 5 if I was wrapping around this way. Keep that in mind, please. Your limits change. So those are my limits there. Which is the outer radius, or the upper function? 2x plus 1, right? Isn't that the outer one? That's this part of the line right here. That's that right there.
Would that be considered inner?
We're revolving this way. If it's that way, it's inner. Yes, Karen. If you're doing this way, it's inner. But watch. Take a disc and start to revolve it like this. This is going to be the outer one. This is going to be the inner one here. Okay? You're always going from the x-axis up. So you pretty much would draw your line and say, what do I hit? That's the furthest one I hit. That's the radius outer. What's the one that's inner? Is this one. That's the radius inner. Okay, so g of x here is the radius outer. F of x is the radius inner. And from this point, we just apply our formula. That's it. It's always about radius outer minus radius inner, those quantities squared. So I got the integral from 0 to 2. Okay, from 0 to 2 of the radius outer minus the radius inner. I can think of this as the integral from 0 to 2 of 2x plus 1 squared. Sorry, thank you. I'm dropping stuff left and right. Minus the radius inner, which in this case was x squared plus 1, quantity squared, dx. Again, the radius outer was our line or linear function. The radius inner was our quadratic function. The only tough part here is doing this by hand, if it was by hand. But a lot of these problems, they're actually given as problems that are not by hand. They're given as calculator problems. All right, now, what happens though, and this is the trickier part now. See how they intersect there? What happens if somebody said, find the volume that comes about by revolving this from -2 to 2? From -2 to 2. So for example here, now I've got this volume also, and I'm also revolving that around the x-axis. Why 2 parts?
Switch it, the outer rim and inner rim switch. So we have to do 2 parts in order to do it.
Yeah, the idea here is that the functions are switching places, aren't they? So if you have, we're not going to do this one, we'll do another example. If you have an example like this, make it more clear. That one's done. I'm not going to do the integral. I'm going to leave it for you guys to work out. Yeah. Again, guys, a lot of the stuff with the integral I'm going to leave for now because you can do it all on your calculator. Okay, there's no use in us just going through that. So here, yeah, let's say we have exponential growth, maybe -1, so starting at the origin, and we have a square root function. So this is radical x, and this is e to the x minus 1. Okay, they both start at the origin. Both of those functions do. And if I asked you, find the solid produced by revolving this around from 0, when are they going to be equal to each other? Oh gosh. Square both sides. That's going to be a mess. 2. It's going to be less than that. Okay. So let's say from 0 to 5. So let's say you're integrating from 0 to 5. Okay? Somewhere between 0 and 5 is this intersection. First of all, how could you find that intersection right away?
The intercept function.
Intercept function. Are you going to do it by hand here? You're not going to be able to do it by hand here, actually. Because if you try to set these equal to each other, well, you can, but it's going to be a real mess. There's going to be one we always do on the calculator. So go to your calculator, please, and y1 and y2, type these functions in. And y1 and y2, type in the functions. That's right. You gotta zoom in a lot.
Right, which is right
Yeah,
there.
that's right. That's the region. Okay. By the way, guys, I'm realizing now we'll go from like 0 to 2, not to 5. But just zoom in. Zoom in near the origin, please. Yeah, or by the region where they intersect. So probably just going to go from like 0 to 2 now that I'm looking at the graph. Let me just look at that one more time. Yeah. Let's say we're going from 0 to 1, not to 5. Let's say we're from 0 to 1. So you want to zoom in a lot, guys. You're going to see this. That if you look from 0 to 1 on your x-axis, you will see that little curve there. Is that pretty much correct now, Karen? So you want to find the intersection of these 2 points, right? So you're going to go to second calc. You're going to go to the intersect function. You can actually find the intersection. So the intersection here, Edgar, what do you got?
5, 5, 7.
I don't care about the y value, right? Doesn't matter, actually. All right. So now, I'm just putting a blank there for the y value. It doesn't matter what the y value is. What should you do with that intersect, again? Because the decimal, it goes on forever. I don't want to lose anything.
Make the
Run to the nearest third.
Okay.
What should I do in my calculator that we've done before when we get an intersect? Store it. So everybody press your intersect, get the actual value of 0.557 on the graph. Then just hit store. Please store that 557 in A.
And then we
Again, I'm telling you now, guys, this is on the test. They actually look to see that people stored it. Okay, so store.
Wait, they look at your calculator.
No.
you
They
have
look,
out
to
to
see,
8.
they look to see the exactness of your answer. And if they see that the answer is off by a little bit, it's because you didn't store it because you rounded. And I'm not joking with that at all.
So
They
you
actually
got
do.
alpha A to safe instead?
Store the intersect in A. You would hit the store A. You would store alpha A, right? Yep, and enter. Oops, you go to. You have to first find your intersection.
I did.
Do it again.
Do
it again.
Charles.
Fine. Enter, enter, again.
Yeah, it came up with that.
Okay, now hit store.
Store.
And hit A, it's alpha A.
Alpha
Enter. Hit go to. No, I'm trying to remember. Guys, how did we store it when we did it on the graph? Was it the home screen? Thank you, Joss. Thank you, it was the home screen. So do the intersect method, then go to the home screen, then store. So hit store now. Alpha A.
It didn't work.
Not alpha A. Enter. So once you find the intersection, second quit to the home screen, then press store alpha A. Or just quit to the home screen after you find the intersection, then press store A.
Yeah, just go to after you,
Well,
not the
you
intersection.
see that there's an intersection there, right?
Store
What I would do
alpha.
is this. I would use a window. Using the super function. I would use a window, yeah. I would go from like negative 0.5 to 1. Okay. And then on the y scale, whatever the line is,
Just like
it's
it don't
0.3, so maybe like negative 0.5 to 0.5. Just so you can see a better picture. Okay? Right. Alright, so that's my lower function. That's my exponential. That's my upper function. I want the intersection. Do the intersection. Fine. As long as you get your answer 3 times, you should be that's fine.
I was doing.
Okay, now intersection quit. Now store. Store. Alpha A. Now A is going to store with that value. Okay? Good. Questions on storage? We good? Storage? Rose? Yes? Okay. All right, so we store the intersection in A. Now, here's where it gets a little bit trickier. Okay, here's where it gets a little bit trickier. Karen, ready? All right, I don't want to miss this. So we have to now revolve this from 0 to 1. We're finding the volume produced from 0 to 1. When I revolve this area right here, which one is the outer radius?
Radical X.
The radical x, right? This is my outer radius. This is my inner radius. But what happens after that?
They switch it.
They switch. Now this is the outer radius, and now this is the inner radius, actually. So when I do this, I have to think of it. Remember when we did the area between two regions and we looked at each of the pieces? We looked at the piece from here to here as one area and there to there. We did two separate integrals. We did upper minus lower to find this area, and then we did this upper minus this lower to find that area. Same thing goes for volume. You got to find the volume of this piece, then find the volume of that piece. So let's do that. Let's write it out. So to write it out, I've got the integral from 0 to A being my intersection, A being my intersection.
We write them on the exam.
If you write A is equal to, or intersection stored in A and you write it like that, absolutely fine. As long as you provide evidence. You have to say that A is the intersection. You say let A be the intersection. That's it. You don't even have to actually put the number down, believe it or not. You can write let A be the intersection, provided it's a calculator problem, you have it stored, then you just integrate from 0 to A, they know what you're talking about.
Now,
Right?
if you just write int instead of for intersection.
No, I would write let A equal the intersection of g of x and f of x, or whatever it is. Write it out as a statement, yeah. Okay? So now we're doing the upper minus the lower, or the outer minus the inner. The outer is radical x, that radius squared, minus the inner radius, which is e to the x minus 1, quantity squared, dx. That's the volume that comes from the first part only. That's the volume that comes from the region R1. If we call the first part R1, this comes from R1 here. Now, if we want to find the volume from R2,
So you add.
we would just add it. Very good, Karen. So call this R2, region 2, and we're going to revolve that now, and we're going to add that to it. So when I revolve region 2 now, though, my outer and my inner have what? Switched. They have switched, okay? Still same thing, exact same process, okay? So we'll say plus
Except it's 8 to 1.
integral, very good, from where? Awesome, A to 1, because now we're going from, remember, we're going from now the intersection, which is A, we called that A, to the end of this graph, which we called 1. Here, which we called 1. So we did from 0 to A, now we're doing from A to 1. So now it's the integral from A to 1 of the reverse. Put a pi out front. Now we've got e to the x minus 1 quantity squared minus radical x quantity squared dx. And just so you know, a lot of the tests nowadays, they don't even ask you to get the answer. They say set up the integral needed to find the volume. You would be done right there. Absolutely. A lot of the tests now, you know what a lot of the tests do? Here's a standard part 2 problem on the test. Find the area between the curve from 0 to 1. So you have to find this area, the actual value, find this area, add them together. That's the first part of the test, or part A. Part B will say something like, find the volume of the solid produced by revolving around the x-axis. Leave it in integral form. That's it. What's the next part going to maybe ask?
But isn't this the,
We did the area between the two. We did the volume around the x-axis.
so that's,
What is it? The y-axis. They're going to then say, also find the volume revolving around the y-axis.
Or set it up.
Or set it up, yeah. So set up the integral. Set up the integral that defines the volume produced by revolving around the y-axis.
Switch the variables.
Okay?
but Mr.
What
Howe,
if you have to give a different,
You have to figure that out. You know that value. Come on. Think about it. If you know the value of the function here is 0, and the value of the function here is 1, you can figure out what you're actually doing now. It's a little bit different, though. It's a little bit trickier. Okay? If you integrate with respect to y, though, what do you have to make sure everything is in terms of in your equation? All y's. So how would I get y here? This is really y equals radical x, right? So we solve for x. That's what that function is, really. So we'd end up using a y squared in our integral somewhere. And we'd have to square that for the radius, y squared squared. Up here, a little bit trickier, right? We're going to get ln in there probably, yeah. So if we had y equal e to the x minus 1, I add the 1. I take the natural log of both sides. And that's what I get. So this would be the function in terms of y. So if I was integrating with respect to y, my e to the x minus 1, I have to turn that into y. That would be inside of my integral somewhere. And this would be inside of my integral. And then I have to say which is outer, which is inner, all that stuff again. In this case, this is inner in the beginning, isn't it? Isn't that one the inner? And what's the outer one? This one here, the red one, is the outer radius. But then what happens again? They switch again. Now the question becomes this. If you're integrating with respect to y, You see how we ignored this part here? Remember we ignored the intersection earlier? Now we need the intersection there. Now we clearly need it, yeah. So we'd have to go from 0 to A, where A, or let's call it B. We'd have to go from 0 to B of the outer minus the inner. Then we'd have to go from B up to whatever this function is of the outer minus the inner, having them switched. Okay, all with respect to y. All with respect to y. Let's do another example of this. Okay, I'll have you try it on your own, maybe.
Yeah, I know.
Okay, try this one on your own.
That was a what?
Are you alright with that?
Let's say we've got. Really, by now? Really?
No, I really no. Like I just need to say.
Oh, 1.
Oh, one.
So let's say we've got. I'm trying to come up with a really good problem here so we can do all 3 of those things we just talked about.
Oh no.
We're going to do all things. We're going to find the error between the regions. We're going to find the solid revolving this way and the solid revolving this way.
All cubic.
So let's see.
Cubic and linear. Or cubic and
Can I see your calculator, Karen? Because that'll make it a lot easier to get a picture.
I already got it. Exactly.
No.
I can breathe.
You're on top line, so then you.
Daddy gave me a
Get it out the way.
They wanted to
Whoa.
know, like,
Screams in the eye.
That video was from how I had a lot of neon lights. Like the guy with the black screen, they were using all the colors. Which I'm surprised he never used the color white. That was pretty bright.
I heard. Hey, don't get it. I heard.
That was like
Pretty straightforward, Christian?
Oh my gosh.
Sure.
Both of you getting good.
Yeah, we talked about that.
Why? That small little territory. Parts of that small little territory. Excuse me. Your territory is probably smaller than what I live. Wait, is it something smaller than what I live? What are you saying? That's still small and tiny. Exactly, that's big. It's like anywhere else but shoot.
Like, what are they doing there?
Because she was talking to because she had a skirt on.
From top of my
Meaning
head,
she had to respond to Jesus.
I can imagine that music tortilla he gets, so you
Oh, hey, John. What's up?
It wasn't a good
Hey,
comment.
what's up?
Nope. Okay.
I
my
In
Jesus.
school,
How's my
in
Jesus?
school, that's where your skirts.
I had an example.
I just want fans that are really skinny.
But not that long.
I would prefer my mom because there's it's like because she's big beagle eyes.
Guys, take out this paper here. 2005 question 1. It's in there somewhere. It might be in your notes. I gave you a copy of it at one point. I'm going to pull it up here. I forgot we had the example.
I can imagine things you go live. You like that music.
It says 2005 question 1.
When did you give us?
This was like a few weeks ago, maybe 2 weeks ago or so.
You never got it.
I don't remember that.
I don't think I got
All right. Well.
Like Jocelyn being talented.
Yeah, she can be a Disney channel. You
Yeah,
can Disney channel
yeah.
stuff. Everybody dictate your lyrics and you can sing it the way they want.
I mean, I seen Jasmine Halloween, so it makes it a little.
Hey, the way they want you.
No, I said they make you sing the way they want
Look
you
at
to.
him, how he done it.
I said I seen you in a Halloween episode of this show. That's what I said.
Where? What is going on?
I don't know. Hard to do it. Well, that's stuff. That is something.
Alright.
You gonna get somebody over a rainbow? Hope he's Irish. Yeah. Wait, that's not cubic.
No, but it's a little bit trickier than a cubic.
And you know the rainbow.
Negative,
You couldn't make the rainbow, you can't go over it. You went through the rainbow. You can't get off the ground.
I don't know which one.
A rainbow is not a horizontal line, like, no, a vertical line.
Alright. If you don't have it with you still, guys, it's fine. You can just write it down. So this other problem is actually given on the test, okay? So, it starts. It says, let f and g be functions given by the following. A quarter plus sine of pi x, and g of x equals 4 to the negative x. Right away, calculator problem. Just look at the functions, right? Just looking at those. Try to find the intersection of those by hand. Good luck. Have fun. Okay? Let R, for anybody, not just you guys, for me too. It's not fun to do this. Let R be the region shaded in the first quadrant closed by the, by the y-axis in the graphs of f and g. Let S be the region shaded in the first quadrant closed by the graphs of f and g as shown in the figure. So, what's going to happen here is we have a sinusoidal wave, right? So there's going to be a lot of intersections or something like this. You'll have a few intersections. They're telling you, just look at these portions. They're giving the graph of this. Then they're saying, find the area of R, find the area of S, which we did. We did it together in class already. We can do it again to show. And then find the volumes generated by revolving it. And I'm going to say, instead of the horizontal line, for now I'm going to say the x-axis. We're going to do horizontal lines and stuff after school today. So for now, let's just write down x-axis.
So the line did the x-axis.
Okay?
Yeah.
No, because that one, the horizontal line was -1. So wouldn't that just mean the same thing over the x-axis on the lower?
Yeah, it's going to be different though. We're going to talk about the day after school. If you revolve something around a longer path, you're going to get more volume out of it. So that's a very different.
That's a longer path.
Yeah, it's a different case because it's, what was it, -1? Yeah,
Yeah.
much longer path. This would be revolving not just around x equals 0, but x equals -1, which would make you go out further. So you get more volume actually out of it. Different answers. All right, so finding the area of R, we're going to do the upper function minus the lower function, right? So for part A, we're going to do the integral from 0 to A of the upper. What's the upper function here in the beginning?
G of x.
Which one's g of x though?
X to the -4? I mean,
4 to the negative x.
Oh, there it is.
Minus the lower function. So that's my area for the first part, but what's A, guys? Intersection, right? Intersection.
You didn't write it. So.
Relax, listen, much. Okay, that's how you want to write this. We're not doing volume. We're not doing volume, we're doing area. No pi. Okay? Again, and nothing squared either, notice that? So, where A is the intersection of F and G. Now, A would be a certain value. You can look that up. It doesn't really matter what it is. If you want to see what the value of A is, A turns out to be 178218. And if you want to check in your calculator, that's what you get. Okay? And see, even on the test, what they do for the actual solution, before the solution begins, they define A as that decimal. I would say let A be the intersection. Absolutely, okay? And you go from 0 to A of g of x minus f of x. Exactly what we did, and you get two different answers. Why are those two different answers? Here's the deal. On a test, they give you a little bit of leeway. They give you a little bit of leeway, God bless you. Because some people don't know about the store function, so they'll keep like 5 or 6 decimals. But you need to keep at least 5 or 6 decimals. Notice to keep 1, 2, 3, 4, 5, 6 decimals. If you didn't do that, if you store it completely, if you store it, you'll get one of these answers. If you round it to these 6 decimals, you'll get the other of the 2 answers. So they accept the answer if you keep enough decimals. But why have to worry about that? Never worry about it. Just store it. It makes it a lot easier on you. You don't worry about how far, how do you know how to round. Okay? Next.
So, but Mr. Howard, when you hit store, on the graph, right?
No, you press, once you find the intersection of the graph, you
Just
press
go
second
to-
quit, then you press store, it'll take the answer from the graph and store it in A.
Alright.
Okay? That's for R. What about for S, guys? What's the only difference going to be here?
Obviously, they're gonna switch
Good. And what are my limits going to be then?
from A to 1.
A to, why 1? Where's 1 coming from?
Hold on.
So what is that? The other intersection. You have to find another intersection. So again, if you call this intersection location A, you would call this intersection location B. So now you're integrating the second part of the upper function minus the lower. This is still area. And I might put,
The second.
yeah, I might put second intersection there. Okay, just to differentiate there. Now, obviously, guys, this 3 points and 3 points, these are worth here, I'm telling you now. This will be worth, the limits here, 0 to A, with this definition is worth 1 point. The integrand is worth the second point. Next part, limits are 1 point, integrand is the second point. Where's the third point going to come from for both these? The answer. Just the answer. The actual answer, nothing else. Again, it's a calculator problem. For each of these, you get 1 point for the correct limits, having them as the intersections, 1 each, that's 1 and 2. Another point for each of these integrands, knowing that they're mixed, if you switch them. The third point, so the point from each of these, the third point, is actually putting down the actual answer for both of them. Okay, which you can easily do on your calculator. Now, let's get to the third part.
We don't have to add them together, right? The areas?
No, we just said find them separately, right? Now, the third part says find the volume of the solid generated when S is revolved around the x-axis, S. Let's make believe it didn't say S. Let's say these regions are.
So these active both now.
I want to try both, because we just did that. That was the emphasis of this problem. So if we took this solid and revolved it around the x-axis, this disk would look like that. This disk would look smaller. This disk will look even smaller, again, because I have the same function over here on this side. This one, I'm going to draw it a little bit better. Hold on.
You got the video.
So I want to draw the exact same shape on this side here.
You draw it.
I got it, yeah. Hold on. Went in, and then this one's going to be coming back around. Starting low.
Yeah, right there.
Intersecting there. Coming back around. Intersecting there. Alright. So, if I were to revolve this piece, this little piece around the axis, I'm going to get this little solid that's produced from only these parts there. But then when I revolve this around here, I'm going to get this big solid here with this little solid missing in the inside. So I'm going to get this like transient shape, or the shape that changes as x changes. Transient means time, really, but something that changes as a function of its distance. So it's going to be like these these big washers, then even bigger washers out here, then even smaller washers in here, and then the solid's going to eventually get to an even smaller washer. So we're going to have this like almost like an empty, what?
Chamber?
Like a spaceship?
Like a vase.
I could see it being that. A chamber, a vase, anything like that. Anything with a hollowed out center.
Why is it a washer?
Okay? Because there's a hollowed out center here. This area here, that's what you gotta watch that video for. This area here, Kenny, is hollowed out. We discussed this yesterday. That's why this area is hollowed out. So it's like taking a cylinder and taking a drill gun and drilling right down the middle and hollowing it out. Because this solid, or this area here, produces a solid around here. But it's that little area that's hollowed out. So you're going to get this weird shape. What we want to do for the volume, though, is to remember the outer radius up here is the upper function. The inner radius is the lower function. But this part, now the outer radius is this, and the inner radius is now this. So let's go ahead and set this up. It's going to be a wild expression. All right.
Oh, yeah.
For the beginning part, we're integrating from 0 to A, right? Yeah. Integrating from 0 to A, thank you, with a pi in front. Upper or outer radius, which in this case, which is the upper function in the beginning here? Which function is this here? Okay, Okay, g of x, which is 4 to the negative x. So we got the outer radius squared, very good, minus the inner radius. The inner radius is just the inner line right here, which is f of x, right? 1/4 plus sine pi x. Remember, what do I do to my radius? Square it. Very good. And dx. That's the volume that is produced. Remember, it's really pi r squared. It's a circle, and there's a lot of these little circles, so we're adding them up, so we're doing an interval. Then, after that, what do we have to do? Tell me the whole thing, go ahead.
Pi from A to B.
We're A and B defined already, obviously.
Then you put negative, no, not negative. You put 1/4 sine pi squared minus 4 to the negative pi squared.
Absolutely right. Very good. Again, the solid produced by this first region is the outer radius minus the inner. Let's go ahead real quick and just look. I'll give you another minute to write. Sorry, now you're writing still. Look at the example from yesterday that showed those shapes, so we're all clear on what we're doing right now. Okay, this is crazy to actually look at by hand. I wouldn't do it that way. So let's actually look at an image here.
What about GeoGebra? They don't do that?
They do. It's a little bit complicated though. I'm going to try and pull something together for you guys this week. I actually started doing it last night. Where is... Oh, there's so much stuff in here, guys. I have so many random stuff. They're random comics half the time that I end up finding.
I never heard of that one.
Alright. So, remember yesterday we started by looking at this image. We said if this image is wrapped around the x-axis, we get this shape that gets bigger and smaller as it goes out like that. And that's the shape that you're seeing down here at the bottom. That's that first one we saw, okay? Now, what you looked at now, what we just saw was having an upper and a lower function. That's the same shape still the same shape. All right, here it is. When we revolved this one around the y-axis, yesterday we did this example, we have this emptiness in the inside here, right? That emptiness was caused by this empty space right here. Same thing happens with the x-axis. Let's see if there's a good example of the x-axis. This one is a little bit different. This is what we're going to do after school today. They're no longer revolving the shape around the x-axis, they're revolving it around the line y equals 4, which is not difficult at all. But the shape that you get here is this hollowed out center here. Because look, if I revolve this region right here that is produced, this is a hollow shell. That's that little circle you see right there at the end. This region right here, this is empty space. This whole thing is empty space. That's the empty space opening. So there's an opening, and then that opening gets smaller. The opening gets smaller, and you can see the shape of the opening, actually, if you look at it closely. That's the shape of the opening in the middle there. Where does that shape come from? That shape comes from this right here. This little line right here is the exact same steepness of this line right here. This curvature of the bottom is the exact same curvature of this bottom. So what you're seeing there, that little dip, that's this right here, really. And then you're taking that and revolving it. And that's why you see the symmetry on the top. But there's like a hole in there, and that hole is getting smaller as it goes through.
Are we recording?
Sure. It's like an annular radius, the idea here, that it's getting smaller and smaller as you go through. So after school today, what we're going to do now is look at the idea where if there's a line at some point along the way, how do we incorporate that? And that's what you asked actually a little while ago. And the idea is that you're going to be swinging it around further. Because if you were just swinging this around there, like around that, then it just produces this one solid right here. But when I swing this even further, I'm going a further distance. And think about a circle. When you go further, when the circumference gets larger, when the radius gets larger, doesn't that circumference actually get bigger, the distance traveled? So the distance this object is going to travel is going to get larger. Thus the volume is going to increase.
Like that. Like the race car.
Yes, that's exactly what it is. Yep, exactly. We did that with centripetal motion or circular motion. Yep, and that's what this is. It's circular motion, but in a different dimension. Let's see other stuff. So if you want to see, guys, take a look one more time. That was the solid produced, but this is what it actually looks like here. So you're getting this shape that's down below. You're revolving it around the line y equals 4, so it's symmetric on the other side. And that's the one disc, or one washer. We said why was it called disc or washer before or something? This is the washer you're producing right here. It's called disc method when there's no hole there. It's just a disc, like a coaster. I would call it coaster method yesterday. This is the washer. So there's a washer there with an opening. So that's the shape you're going to see that produces.
Did they make that? Did they make the name
You're
washer?
still going to do inner and outer and all that kind of stuff, but it's going to be a little more complicated.
No, I know the tool, but I was going to ask, did they make the word washer from the tool, or they made the word washer from the tool?
They use the word washer in calculus because of the object itself as a washer.
Yeah. So yeah, so which
Yeah,
is an ask which one came first? Washer method or
Well, washer was used to be called an annular disc.
I don't know. Maybe I'm not sure. But you know, the tool with the washer or screws.
I don't know, Kenny. I'm not sure which of those two came first.